So welcome everybody to our Engineers Ireland Biomedical Engineering Division lecture today. We're absolutely delighted to have Professor Peter McHugh from the University of Galway joining us today. And Peter is going to speak to us today about biomedical engineering, an outstanding success story for Ireland, one academic's perspective. So a little bit about Peter. So Peter has a bachelor's degree in mechanical engineering from UCG and postgraduate degrees from Brown University in the USA. He's also a member of the Royal Irish Academy, a fellow of Engineers Ireland, and he has over 30 years of experience as an educator and a researcher in engineering, and has been one of the pioneers nationally in the development of biomedical engineering since the mid-1990s. His particular research expertise is in computational modeling in biomedical engineering, with a focus on the biomechanics of tissue and medical implants and devices. He has published widely and has received a Doctor of Science on published work in 2021 from the National University of Ireland. So I'm absolutely delighted to hand over now for Peter to begin his presentation today.
So thank you very much, Suzanne and the team at Engineers Ireland. It's a real honour to be asked to talk to you today, and thanks very much for people connecting in virtually to the session today. This is very much my perspective and a personal journey through biomedical engineering in Ireland as the years have passed, and I hope I can flesh out some of those points for you today. Getting started, I felt it'd be nice to sort of define what biomedical engineering is, and I'm using the term BME, the acronym BME as well. Biomedical engineering can be considered a sort of a short version of a definition would be the application of engineering tools and analysis to problems in medicine. And a longer title that I really like from the Whitaker Foundation from some years back: biomedical engineering is a discipline that advances knowledge in engineering, biology and medicine, and improves human health through cross-disciplinary activities that integrate the engineering sciences with biomedical science and clinical practice. So everything that's important about it gets a mention there. So this is the fantastic work that biomedical engineers do and biomedical engineering students are learning about. And of course, it's multidisciplinary. It links between academia, clinicians, and industry. So just starting at the start and thinking back to the early days, you know, from my perspective, when did things start? What do I remember? Looking back, biomedical engineering, as I understand it, or the community that I'm working in today, really started around in Ireland in the 1980s. And if we look at research, things started in the 1980s, and you know, one of the starting points really was what was happening at TCD, UCD, and RCSI. And I'm thinking of people back in the day: David Taylor, Brendan McCormick, Clive Lee, who set up the Bioengineering Research Centre back in the 1980s and initiated the Bioengineering Design Forum, bringing engineers and clinicians together. And it was mostly at the time focused around orthopedics. But, you know, that was the nucleus of where things started. In the 1990s, things began to ramp up for a lot of reasons. Here in Galway, we got big into things. Our collaborators and friends in UL got into things as well, and indeed across the country, DCU, UCC, the Institutes of Technology, and in Northern Ireland as well. The communities began to develop. And, you know, one of the great ways that I like to look at this particular line of history is something called the Bioengineering in Ireland, the BINI conference that we hold every year, under the auspices of the Royal Academy of Medicine in Ireland section of bioengineering, which was set up in 1994. And if you just look back in 1995, the first one of these had only 40 delegates. We had our 28th conference earlier this year, hosted by RCSI, and there were 210 delegates. So that just gives you an indication of how things have developed. So into this particular developmental environment, you know, where did I fit? Well, of course, like a lot of people of my vintage in the business, we didn't start out doing this at all. We did other things. We were doing something else. And I had come back from the USA in 1992, and I had done a PhD in computational micromechanics of materials, looking at metal ceramic composites for the auto and aerospace industry. We had a project funded by the Ford Motor Company. We're looking at brake discs, and we're looking at these advanced materials and aluminium matrix reinforced with silicon carbide particles, and you know, looking at the modeling of that and looking at the micromechanics, looking here, finite element modeling, looking at the deformation of the soft aluminium. And that's important because I'll come back to that later, but it wasn't biomedical engineering. I came back as a lecturer to mechanical engineering in Galway in 1991, and my first explorations in biomedical engineering did happen in the 90s. In 1995, I started looking at angioplastic catheters in collaboration with C.R. Bard, who was based in Galway at the time, and my colleague at the time, Crothúr O'Brady, and we were looking at finite element and experimental bits to generate a virtual experiment, what you'd call an in silico study nowadays. So this was the first, my first sortie into biomedical engineering. And if we just look at a little bit of this for a second, Brendan Caniff was our student at the time, and he looked at creating a physical test cell, looking at a pig heart, using the lost wax approach to generate a physical model of the arteries, then generated a physical model from that out of silicone, etc. And he also did finite element simulations. Just go back, laser pointer, and can run it here. And this was done 28 years ago. And these simulations still look very, very fresh. So this was the first thing that we did, looking at the insertion of a catheter into a tortuous artery. And one of the nice things about this study was, back in the day, formative years, we got a very, very good correspondence between experiment and modeling. You can see the experimental curves, so the push force, when you're pushing the catheter through this tortuous artery, you can see the push force, and the blue line then is the finite element simulation. So we were very proud of that, and that was the first work of mine in biomedical engineering back in the day. So then what did I do? I went to sabbatical. I went to sabbatical in Germany in 1996 to one of the Fraunhofer institutes in Freiburg, and I also went to Aachen, and I saw the way that biomedical engineering was beginning to develop in Europe as well. And then that was perfect timing, because when I came back to Ireland after sabbatical, the funding landscape in Ireland changed, and changed forever. People maybe don't realize, but back in the early to mid 90s, there was really no money for research in Ireland. Very, very little money there. It was very hard to get, and people had to survive on small amounts of funding. That changed in the late 90s, and the first big thing that happened was the HEA released PRTLI, the Program for Research in Third Level Institutes. Okay, and their initial budget was 605 million euro. That was unheard of. The universities went at this, and I was in a very, very good position to get involved in this. And I was one of the original team back in those years in 1998 in Galway that went after what was called PRTLI 0, the very first call, and PRTLI 1 in 1999. And I was one of a three-person group, subgroup. This is where multidisciplinarity started for me. I was the engineer working with the chemist, Liam Carroll, God rest him, and an anatomist, Brendan Wilkins. And we got together, we were put together to work together to develop a proposal to develop this particular area, biomedical engineering science. And this led to the National Centre of Biomedical Engineering Science being established in Galway, the NCBES. And you'll see down here in the bottom right, this was the ultimate home of that major funding generated, this building, the Orbson building, where it started. And also our distinguished chair today, Susanna O'Rourke, was a postdoc with us in those formative years when we were developing all of this. So from this developmental phase, what happened in Galway and what happened across the country? Lots of things happened. PRTLI continued, more money flowed. PRTLI Cycle 3 happened in 2001, and that was significant because we in Galway were involved in a number of projects. We were involved in a major project with TCD, and that led to the establishment of the Trinity Centre for Bioengineering. We were also involved in a parallel project with UL, Tim McLaughlin and the guys in UL, and that fed into the development of the Caber Research Institute at UL. And a name that I forgot to mention back the way, of course, in all this developmental years was Paddy Prendergast in TCD, and he and I led this collaborative project in PRTLI 3 that led to the establishment of the Trinity Centre of Bioengineering as the main partner. PRTLI 5 came a number of years after that. And one of the main things about this, in addition to funding for capital and all the rest and buildings, was the structured PhD program, where you developed new PhD programs that would have modules in there, taught modules that people could take and give them a greater complexion on their learning at the end of the day, modules and research. And we set up here the Biomedical Engineering and Regenerative Medicine BMERM program that was a University of Galway and UL collaboration. PRTLI was very influential. I was involved in that heavily, as you can see, over the years, and we developed a lot of research projects and a lot of good things from that. And timing was all important. Of course, in parallel with all of that, what was the other major force in the country that happened around the same time? SFI came into existence. It was initiated in 2000, and it had an initial budget of 646 million. Once again, unheard of amounts of money. And you know, they funded a lot of individuals in research, but they funded research centres. And the CSETs, the Centres for Science and Engineering Technology, came along in 2003. Remedy was based at NUI Galway, the Regenerative Medicine Institute, and I was involved in that. CRON was based at Trinity, and there were other institutes. And then the SFI research centres came along in 2012. QRAM was based at Galway, led by my colleague Abby Pandit. And CRON evolved into the Amber Centre at TCD. And of course, there are lots of other centres, and I'm involved in the QRAM project. And of course, it's not just about PRTLI and SFI. You know, there have been other funding sources, but before PRTLI and before SFI, they were hard to get. Enterprise Ireland, of course, funded research in the country. The HRB did, and also Horizon 2020, moving on to Horizon Europe now, that funded research as well. And it might interest people to know that there were other important developments as well. The Irish Research Council, that a lot of us involved in, the European Research Council that has funded a lot of research. These came along in these years, in the noughties. ERCSET was established in 2001, and the ERCs were established in 2007. And very important for my kind of work in the whole area of computation and modelling, ICHEC, the Irish Centre for High-End Computing, was established in 2005, and that's been a game changer as well, allowing us wanting to do advanced computing to do significant work in biomedical engineering and in lots of other areas. So there is a little timeline in relation to research and research developments and who some of the major players were. It wasn't just about research, of course. Education is important. Of course, we educate PhD students through research. Yes, we do that. But of course, educational programs have to come back to the undergraduate level. And we were pioneers at NUI Galway in that we established the first BE, Bachelor of Engineering in Biomedical Engineering, back in 1997. And we established it as a stream in the third year mechanical engineering program. And these guys graduated in 99. And then our first year intake in biomedical engineering happened in 1998. And these graduated in 2002. And we had a very, very nice 20th anniversary celebration last summer, celebrating this. My colleague Leisha McNamara organised this with the alumni office, and we had invited all our alumni back and the university management, and we had a panel discussion of some people that have done very interesting things. Ellen Roach, a professor in MIT, for example, Claire Lillis in Aerogen, Adrian McNamara, and Brendan Gallagher, working in Medtronic, Adrian McNamara working in Boston Scientific, to give of their experiences. And it was a wonderful thing to be able to do, and it didn't feel like 20 years, I can tell you that. I said this was pioneering. We were the first biomedical BE degree program to be accredited back in 2004, and we've full accreditation since then. But I think I titled this presentation an outstanding success story. You can show photographs, etc., and say nice things, but hard data in the end of the day. Is this thing, has it been successful? We've seen it successful in research. Of course we have, with all the projects that have happened. But in education as well, it's absolutely mushroomed. Here is the student numbers in fourth year. I took fourth year of the biomedical engineering program at Galway, and the growth of this over the years. From a handful back at the start in the early years, we've grown to an average about 70 students a year, which makes up over 20% of the students of the whole School of Engineering at NUI Galway. And we have a total graduate output now at this point of 799 students, 799 graduates out in the workforce. I was tempted to say 800 to round it off for the presentation today, but I said, no, I have to take the accurate engineering approach, and I left it at 799. Biomedical engineering has been fantastic in the gender balance. We've had 40% female students, 60% male in our cohort over the years, and a strong income, strong standards coming in, high CAO points. That's the bachelor's program. But of course, those of us in the educational arena know that we have now very much moved into the area of the masters in engineering, the MEs, the MEngs in engineering, bringing engineering graduates to the year 5, to the master standard. That is the new paradigm, and we're all bought into that now in the country. In Galway, we introduced a 1-year add-on ME in biomedical engineering in 2013. And we reconfigured that into a 5-year integrated master's in 2019, with the first group of those now in their 5th year with us. And again, like those undergrad numbers, the master's numbers have gone up as well. You can see the top number there. This particular year, we have over 50 in the class, which is the vast majority of our BE students are now staying with us to do the ME and going to the fully accredited master's level. And we've also launched an MSc in biomedical engineering for international students. That's growing very well. And it might be interesting to see this. We have also launched this year the Physicianeer program. My colleague Ted Vaughan and our clinician colleague Derek O'Keefe have put this program together. A medical degree, the MB-BCH-BAO, and BE in biomedical engineering. So we were hoping this will grow well into the future. And it's not only this happening in Galway. This is my story, the numbers I know close to heart, because I've been involved in the development of all of this. But across the country, in preparation for today, I looked across the island at programs in biomedical engineering. So this is happening all over the country. From a standing start 20 years ago, now there are 9 bachelor's programs across the country and 7 taught master's programs, bringing people to the ME and Eng level across the country. So this is fantastic for our sector, for graduates, for future employment, and for feeding into research so that we can do the new novel things into the future. So what I thought, I've talked a bit about the research developments, and I've talked a bit about the educational developments. I just want to come back to myself just for a minute and look at my own particular timelines in going through all of this. How did I evolve through all of this? As I said in the start, I started as a lecturer in mechanical engineering in Galway in 1991. And I went through the ranks. I was promoted to personal professor in mechanical and biomedical engineering in 2004. And I had the honor then in 2007 of being appointed the first established professor of biomedical engineering in NUI Galway, or University of Galway as we're calling it now. The first time that the chair had been established separately in its own right to the other engineering professorships, and I was lucky enough to get that particular slot at the time. In 2011, I put together from the research activities that we had here in the whole biomechanics medical device modeling area, what we call the Biomechanics Research Centre, Biomech, within the auspices of the NCBES. And that has become very successful. And then the role, which is my present role, the role I'm talking to you today from as head of discipline of biomedical engineering. What does this mean? Well, the year 2013 was very influential because that was the year that NUI Galway split out biomedical engineering as a separate discipline. What I mean by that is a separate department of engineering in its own right, separated that out from its original home in mechanical engineering, because that's where I was before. We separated it out as a separate discipline of biomedical engineering with 6 members to start, 6 academic staff members to start, and I had the honor again of being the head of discipline there. Then, as the years passed a little bit, I moved over to the dark side for a couple of years. I went over and I was interested in management and leadership, and I became the Dean of Engineering and Informatics from 2016 to 2019, and then our colleges merged together. The College of Engineering and Informatics merged with the College of Science to create the new College of Science and Engineering. That happened in 2019, and after that, for a couple of years, I was the head of the new School of Engineering. So I spent time in that leadership and management role also. But looking at all of this, in particular, the biomedical engineering discipline and the development of the biomedical engineering discipline, one thing I'm particularly proud of is how we've been able to grow this over the years. We're really fortunate in Galway what we've been able to do. And from a start in 2013 with 6 academic staff members, we've now grown this to 17 academic staff members. And our support staff as well, Aisling, Juan and Maya. Also, I'm not going to go through all the names. You can see them there. A lot of them you will know. So it's not just research that's grown or student numbers that grown. We've also been able to grow what we are doing at Galway and our person power, which is really formidable. We have scale at this stage. And all of these people are highly research active, winning awards across the board. And just to give you an idea of some of our numbers, at the moment we have 68 PhD students, 18 postdocs, and the group have over the years since the discipline was set up produced 120 PhD graduates. So that is very substantial. And I talked about Biomech, our biomechanics research center that I initially pulled together in 2011, but it's really taken on its own life among the members of the group, and we won the MedTech Rising Award from the Irish MedTech Association, Academic Contribution to MedTech Award in 2021 for our activities, in particular a core project between my colleague Ted Vaughan and Boston Scientific was the core part of this. And of course, I showed you a picture before of the Orbson building, but it's not just about the Orbson building. Our numbers and activities at Galway have grown, and this has happened all over the country. It's not just Galway. The building I'm speaking to you from today is our wonderful Alice Perry Engineering building that was opened in 2012. And also our activities have overlapped into the new Biosciences Research Building on campus and the Lamb Institute on campus at the hospital. And that is a characteristic of what we do. As I'm saying, you know, it's about academics, clinicians, and industry people working together. And the Lamb Institute, based on the hospital, shows that we do collaborate very closely with our clinical colleagues in research and in education in terms of the programs that we generate. So I talked a bit about research, a bit about education, about our university developments. But of course, what about the other huge ingredient, the other very important thing making this triumvirate of activities, the education, the academics, the clinicians, and the industry? You know, what about the industry? The other part of the fantastic success story in Ireland is the Irish medtech industry. This is absolutely enormous. And looking back and doing a little bit of research for the presentation today, I looked back at some of the reports and the literature, etc., that I could find, and my own recollections. You know, there have been medtech companies in Ireland since the 60s and 70s. Companies like Biomedical, they've been here for a long time. The 80s, things began to grow. C.R. Bard started in Galway in 1982. Craigana started in Galway in 1980. And we've seen, but the main rapid growth has been since the 1990s. And here's a little table that I pulled together from a number of sources that you see down at the bottom of the screen there. Look at some of this data. It's incredible. Back in 2004, the industry had 25,000 employees, 140 companies, and an export value per annum of 6 million. Look at what that has grown to as of last year. 42,000 employees, which is 1.5 of the whole national employment number. 1.5% of every worker in Ireland, in this country, is working in the medtech industry, that's a huge number. The 140 has grown to 450 companies, and a lot of these are homegrown, indigenous companies that have grown up working with the multinational companies. And a large percentage of them, 4 out of 5 of these companies are SMEs. Partly, some of them startup companies that have been started up from with our own people. And the export per annum have doubled to 12.6 billion euro per annum. A couple of facts about this. Now, and for quite a while, Ireland is one of 5 global medtech hubs, 5 locations across the world that are noted for medtech. Ireland is one of those. That's an amazing thing. 14 out of 15 of the top global companies are based here. We're the world's largest exporter of stents and the second largest medtech exporter in Europe overall. Germany, a much bigger country, is bigger, but we're the second largest medtech exporter in Europe. These numbers are unbelievable, what has happened in the country. And of course, it didn't happen on its own. It's a fertile environment where academics, clinicians, our industry are all working together to make this happen. And in all of this, I have to give a shout out to colleagues and a group of people that have been very, very helpful and hugely influential and hugely helpful in the development of this over the years. The Irish MedTech Association, formerly back in the day when I knew them first known as the Irish Medical Devices Association, IMDA. I'm talking about Sharon Higgins and Sinead Keogh. Wonderful people steering all of this ship and establish an excellent interaction with between academia, clinicians, and the industry. And also, I should mention Engineers Ireland. I don't have their logo on the screen here, but Engineers Ireland Biomedical Division, that over the years have been another hub of linkage between the various important sectors, and long may that continue. So here's a collage of company logos. What is this? What is this slide? This is a slide of some of the industry partners that we in Galway now and have built up over the years collaborate with in our research and in our education in biomedical engineering. And that interaction is fantastic. And most of these companies that you see here are based in Galway. So Galway, we've been blessed in Galway with a local within the country, in the west of Ireland and Galway region, a very, very strong medtech hub or medtech cluster. And, you know, we work with these companies across the board, from something as simple but crucially important as student work placement, through teaching contributions to our programs, all the way up to major research collaborations, feeding into large SFI and European projects, etc. And also, of course, graduate employment. Our graduates, all of these 799 people have to be employed somewhere, employed in the industry. And of course, some of the graduates going on to set up their own industries, the startup companies, which are becoming more and more common, and people coming out with the confidence and knowledge to do that quite a lot. As I said, I feel we've been particularly blessed in the Galway region, and indeed we have, and that's for very many reasons. One of them is that we've had a group here locally of medtech entrepreneurs, and a number of them, you can see in the photograph here, were honoured by the University of Galway back in 2016 at an honorary conferring. John O'Shaughnessy, John O'Dea, Helen Ryan, Ian Quinn, God rest him, he's passed on now, Paul Gilson, and John Power. These people, local and national entrepreneurs that have really worked over the years to push the development of this industry, and have worked hand in glove with us in the universities to do that. I can think back, I was talking about the early days back in the mid-90s, when we were starting to develop our biomedical engineering program. What did we do? We brought these guys into our meetings and worked with them and found out, what does the industry need? What would your graduates need? What are the skills that they need that you would employ them in the industry, etc. And, you know, John O'Dea, Paul Gilson, Ian Quinn, John Power in particular, were hugely influential in that, working with us. Also another ingredient run now out of Galway is the BioInnovate program, which was initiated by my colleague in the discipline of biomedical engineering, my own PhD graduate from back in the day, Mark Bruzzi. And this is where there's an intimate link between academia, clinicians, and industry to get new ideas coming out from the clinical arena, working with academics, and to come up with new business ideas, patents, and startup businesses that could take this whole thing forward. And that has been hugely successful over the years. So at this particular point, I've been talking a lot about generalities. I wanted just to come back to myself a little bit, and I wanted to spend a few minutes talking about some of my own research. Now, you know, I've been at this for a fair while, you know, since my days back working with C.R. Bard, starting out of that project. And so lots of things have happened. What I'm focusing on today, actually, just three examples, very quick three examples, trying to show some kind of timeline on the way things go, focused on coronary stents, because I've spent a lot of time working on this over the years. And I was telling you initially that, you know, I started working with C.R. Bard back in the day, looking at angioplastic catheters. Of course, stents are the other part of this, where you've got the stent on the catheter, the stent being implanted. And, you know, you can see here the little cartoon of the stent, the metal stent. Back in the day, that would have originally been 316L stainless steel, inflated on the balloon removed, and the stent remaining in place. And these stents undergo a lot of plastic deformation, an awful lot of deformation when they have to do this, and that requires special material properties. And of course, they come in lots of flavors and designs over the years. And they're, as I say, they're very small. Here you see one, the coronary stents at the top of a fingertip in the undeployed and then the expanded state. And you know, one of the reasons I show you this is because, you know, life is funny. You can plan things, but then things just happen, and you have to be able to respond to that. For me, in my whole development in biomedical engineering, there was one big eureka moment, and this was it. This was the eureka moment. Let me try to explain what this is. This is a picture of a single strut from a stainless steel stent, and you can see the size of there, 70 microns across, that colleagues in Medtronic came into me back in '99. I remember it well, back in '99. Well, I should say I remember it well once I got up off the floor. Once I saw this picture first, I said I couldn't believe it. I nearly fell off my chair, and I'll explain to you why in a minute. This is a stainless steel strut in a micrograph, And, you know, these are individual grains of stainless steel that make up the microstructure. Anybody that studied an engineering materials course back in the day will recognize microstructures and grain structures in a metal. And this was a eureka moment for me. Why? Why was this a eureka moment for me? Because I had seen this before. I had seen this kind of thing before. They came into me and showed me this picture, and they were interested in, you know, Peter, could somebody analyze this for us? Could somebody look at these kind of structures and tell us what is the relationship between the grain size, the microstructure, and the mechanical properties, in particular the ductility? Could somebody tell us about that? How important is the grain size? And, you know, could you model it? Right? We know you do finite element models. We've seen you doing the catheters. Can you do something with this? And I just couldn't believe it. Why? Because this is exactly what I had done for my PhD only a few years before with a different material in the USA. And what's this picture here? This picture here shows you aluminium alloy. That's a microstructure of an aluminium alloy. And here is this same microstructure, the same sample, when it has been deformed. In this particular case, it's been crushed in the vertical direction, right? It's been significantly plastically deformed, significant amount of deformation, which is consistent with what you have to do to a stent. You have to deform the struts in the stent a significant amount to get them to stay open, okay? You know, so this was experimental work that was done by a co-PhD student, or one of my PhD student colleagues in Brown University at the time. And what I'm showing you here is, what does this look like? What are the arrows? Well, each of these is an individual grain of steel, okay, with a crystal structure. This crystal structure here, what's this? This is a face-centered cubic crystal structure, and the steel deforms, dislocation motion, but it deforms by the flow or the sliding of these planes, these crystal planes over one another. And you can see the planes here. You can see that different crystals strain and slip and slide in different ways. Here's another grain with perhaps a different crystal orientation, and the crystal orientations are different in each grain, and you can see the sliding, you can see the slip lines, as they call them, the inhomogeneous deformation, the localized deformation. This is what goes on. And for my PhD, I had developed finite element models to model this very thing. And I will say, and I guess I can say it because I'm speaking now, I was the only person in the country at the time that was able to do this. So it came to me, and I just had to grasp the opportunity once I got up off the floor after falling off my chair, okay? So here's a finite element simulation of something I did for my PhD. This is a regular crystal geometry hexagons, and then modeling with what we call crystal plasticity theory, where you could, in maths, you could represent the sliding of these crystal planes over one another, and you could reorient the crystal structure from grain to grain. You can see each one is doing a different thing. And I said yes to the guys in Medtronic. I can model this. I know what to do. And I went with it. And then we developed a project then funded by Enterprise Ireland and Medtronic, and bringing in Bruce Murphy, who was a postdoc with us at the time. He did this work looking at the struts. Here's the stainless steel strut again. And the first thing we did experiments to find out, to answer their question, is there a size effect? Does the grain size matter? Does the size of these sample matter? And of course, it does. We did tensile, Bruce did tensile, we did tensile testing on these, and here's the stress strain curve. And you can see, it's a little blurry, but you can see, you know, for these struts, the thinner you make them, the less ductile they become. A 60 micron strut failed after 20% strain, where a 500 micron strut went to over 50% before it failed. Okay, and we then showed, as you can see on the plot at the bottom here, the ductility size effect. Okay, the thinner the struts, the worse they were. And it was important to show this because this showed that the mechanical properties of these sorts of structures, these very small structures where grains were becoming, the individual grains were becoming important, do depend on the size. Normally in engineering, when we think of mechanical properties, they're just a material has mechanical properties. Here we're saying it depends on the size. So it depends on the size. And if you're down at the level of a single strut in a stent, The properties of that are going to depend on how thin it is. They will not necessarily be the same as the global properties. So this was very useful. But then, of course, this was experiment. Could we model this? And could we explain why this was happening? And then, yes, we did. And over the course of a couple of student projects, Pádraig Savage, first of all, Frank Harwood did his PhD on this, and later James Grogan did this as part of his PhD. We studied this using the crystal plasticity that I talked about, and we were able to understand what was going on. So here's the real strut again, and then we generated here, you can see two models that were generated. This is a random structure, random grain structure, and a regular grain structure. Turns out in these particular models, the structure, the grain structure itself, not really very important. You get the same effect. The important thing is the individual grains. The individual grains have to have their orientations of the crystal inside them differently oriented or randomly oriented, as you would have in practice. Okay, with that representing reality, then the magic happens. Here's one of the simulations of finite element boundary conditions applied. We applied a stretch, and what you see here are two little simulations happening. Okay, these are little GIFs right from the simulations that we ran. The top one, okay, the top one has a thin strut with about 3 or 4 grains across the thickness. Okay, the bottom one is a much thicker strut with about 20 grains across the thickness. It's the same material. The actual grain size on average is the same, but just the number of grains is different. Okay, you can see that they do very different things. The one on the top with the small number of grains doesn't stretch as far before it begins to fail. You can see necking happening here and failure happening here. This one, the bigger strut, goes further. And even at the end of this little simulation, it hasn't necked and failed yet. What's going on? Why is this the case? It's happening because of what we call plastic constraint. This is what we uncovered, plastic constraint. Here in the top sample, you'll have a grain, and the different grains are oriented in different ways. Some of them will slip very easily, others will be very difficult to slip. The ones that are oriented in a favorable way to slip don't have very many grains around them. They can slip easily without much support. They're not constrained, so the thing can fail easily. Down here, you'll have grains that are favorably oriented for slip, yes, but there's loads of grain around them to hold them in place. So here we see the effect. We've been able to produce the effect, and here, this is our graph. This is the graph that we produced, and it turns out that the key ingredient is not the actual grain size itself, but the number of grains across the thickness. The size of the grain divided by, or the thickness of the strut divided by the size of the grain, or the thickness of the grain, the size of the grain. That's really the ingredient. And of course, you can see that when we put our computational models back on the experimental data, we were able to pick up the trend. We were able to use this to explain this particular phenomenon, and we were very happy with that. And this was for stainless steel, but where we brought this to, or one of the outcomes of this was, we were able to do the same thing for cobalt chromium, which is the more modern stent material. The same kind of thing goes on. And this formula here, I'm not going to go through equations, but I just want to show you that we had a formula. We were able to fit the data. We were able to come up with the design formula that allowed us to relate the failure strain to the size of the strut, or in particular, the number of grains across the thickness. And that was something that emanated from a eureka moment. I wouldn't have got into this at all unless those guys from Medtronic came into me and showed me that picture on the day, and we could do something significant afterwards. In the stent team, then, where did we go with that? My second example is the bioresorbable stent. We got into bioresorbable stents then. This is a stainless steel stent, and this is a magnesium alloy stent. And, this is histology, where you're looking at a section through the artery. With the stent in place, you can see a cross section through a stainless steel stent strut there. This is neointima that's grown into the artery lumen. And you can see the magnesium one, where the magnesium has practically disappeared after a period of time. We wanted to model this. And with James Grogan, a wonderful PhD student that I had the honor of working with for a number of years, he, as part of his PhD, developed the pitting developed a corrosion model, or a model that picks up this, a model that represents this process. Magnesium, how does it degrade? It degrades by corrosion. It degrades by surface corrosion, and it does this in a pitting fashion. What's called pitting corrosion. Localized pits on the surface form, and then the material corrodes. A chemical reaction happens. The magnesium turns into magnesium chloride and other things and gets washed away. The magnesium goes away through that process. So he developed this model, a game changer at the time as well, to be able to do this. And you can see one of the nice little simulations here. Of course, that we want to apply this to stents. Okay, so what I'm showing you first is simulations James did of the angioplasty procedure. Here's a generic stent being expanded on the balloon. So that's the expansion step. Next, we've got the recoil step, where the balloon is deflated and removed, and the stent remains in place. And then he implemented the corrosion model in the stent models. So this is what's happening as the corrosion is happening. Now, on the left, you've got the original way. People were modeling stent corrosion before. Yes, they were, but they were not modeling it in a realistic way. They were modeling it using what you might call uniform corrosion, just assuming that the material was being uniformly degraded away. That's not what happens. So this is the uniform corrosion model on the left, and on the right is the model with the pitting corrosion, a model implemented in it, calibrated and validated against experimental data. And you can see the way the stent collapses, pits form in different locations, and the stent collapses in a much more irregular fashion. Is this realistic? Do you see this? Well, you actually do. This is up here, you've got pictures of our stent. This is our stent model. And you can see that, with the pitting corrosion model, typically we get corrosion and degradation happening at the hinges in the stent and sometimes on the straight struts. Do you see this? Well, yes, we look through the literature where you can see that very thing happening in images, medical images of implanted magnesium stents. You can see there the hinge degrading in that particular location. Here you can see the straight strut degrading. And you can see in this particular image as well, an initially perfect stent collapsing into a disorganized structure with this pitting degradation going on. And you can see here that we were able to predict what is seen experimentally is the fact that if you use the uniform corrosion prediction, you get a relatively slow stent degradation rate, whereas with the pitting corrosion model, you get the more realistic, more rapid stent degradation rate that is seen. And this work is ongoing. Using these models is ongoing, and this work that we did prompted and spawned a very, very interesting collaboration that we've had now over the last number of years with a company called Miotech. Alex Kopp and his colleagues in Germany who make magnesium for medical device applications. And they're very, very interested in what we're doing, and there are collaborations going on with them to look at how the model could help in the design of better implanted magnesium devices, and in particular to give us information around how this degradation could be slowed down, because that's one of the problems with the magnesium stent, is the rapid degradation picked up by our model. And my colleague Teg Vaughan and Conal Quinn, PhD student, I'm collaborating with them on the further development of the model, and Conal has just a paper out in JMBBM in the last couple of months on that, further developing the Grogan model. Finally, my last example, coming to the end, is even taking all of this further. I showed you a picture a few minutes ago to show you, here is the magnesium stent. This is histology through the artery, and you can see the neo-intima. You can see the intima growing in, and you can see the magnesium. When I showed you the pictures before, there was no intima, there was no neo-intima, there was none of this regrowth. We wanted to try and model that, and that's what we did. Enda Boland did his PhD on this, finished up relatively recently, and to this we did a very complicated thing. We took a multi-physics approach. We combined the corrosion model. I have to get back to my, 1 second, get back to my pointer. We combined the corrosion model that you can see here, the pitting corrosion model, with a model of the artery, and the arrow there is representing the fact that we represented fluid flow, CFD blood flow through the lumen, coupled with the stent expanded into an elastic artery representing tissue properties and the biodegradable stent, and using all of this to generate neointima, to use a neointima generation algorithm. And that's what we did to produce simulations like this. Here you can see a simulation where the pink is the neointima growing over the stent struts. And you can see that the artery is collapsing a little bit. Why is that happening? That's happening because the stent struts are decaying. They're degrading over time. So we have the whole thing together. You know, does this make any sense? Is something like this seen? Well, we're getting very, very good. So far we've got very good indications from our modeling. Here you can see some snapshots through the model as the neointima is forming, and you can see here, let me get my pen again, excuse me, laser pointer, go back. Here, if we look at the this particular stage, here you've got the proximal end. Remember, the blood is flowing left to right. So here you've got the proximal end, here you've got the distal end, showing that the preferential neointima formation in the proximal end. And that's what we see in experimentally. We saw this data, looked that at the proximal end of the stent, they were showing greater neointimal formation relative to the distal end, and this was in a porcine model. And that's one of the interesting results coming out of the modeling. And we can look at the mechanisms. The model allows you to look at mechanisms for this to happen. And this work is ongoing and it's very exciting. So you know, that's bringing me to, I can see the time is passing. So that's bringing me to the end now of just my little snapshot through the research. And I want to finish today with two final slides. The first one is to talk about future perspectives, and then a few things on lessons learned. Future perspectives. What do I see into the future? Well, it's a no-brainer. Biomedical engineering is a thriving area. The future is extremely bright for biomedical engineering and medtech. Industry growth, we see lots of reports. Cerenovus, Boston Scientific, Medtronic, lots of other companies, startup companies investing in the area. There's going to be further industrial growth, and that will fuel the need for graduates, more graduates, and the need for more research, this symbiotic relationship between the two. This stands to grow even further in Ireland. Ireland is poised to make a real international impact, even more than we have in this area. I think there's going to be greater multidisciplinarity in biomedical engineering. I didn't talk too much about bioelectronics in my discussion today. I haven't done an awful lot of that over my time. What I've been talking to you today is pretty much the biomechanics, medical devices, biomaterials side of the house, at least in terms of the research. But of course, it's critically important that this happens, leading to, you know, implants and devices that are smart, that give out more information than heretofore. That's the thing into the future. And of course, another no-brainer is the link with data science. Data is all around us. Artificial intelligence, machine learning, dealing with large data sets, large clinical data sets, large imaging data sets. You know, we as biomedical engineers have to learn more of that and become more conversant in that area. And, you know, in the modeling terms, leading to something called the digital twin, where you have a virtual environment where in real time there is a digital model of a system that's able to respond and give predictions and analysis in real time. That's one of something that we can aspire to. And a lot of the models that I'm showing you up to now, using iCheck and lots of other things, they're hugely advanced and hugely detailed in what they do, but they're not necessarily real time. They won't happen instantly when you need them. It takes a long time to run some of these things. The future has to be about the real-time digital twin. And related to that, the whole area of modeling brings us into the in silico clinical trials. Now we have clinical trials. How can we use modeling to do some of that, to be for the models to be validated and accepted sufficiently in the industry for further device design and regulatory approval? There needs to be more impact, and there's plenty of opportunities for that. So, finally, lessons learned. There's always new horizons. Even an elderly individual like me can see that there are new problems to solve all the time and new technologies to create. And also to make progress, you need two things. What has my path told me? That it's important to have a strategy. It's important to have a roadmap. Yes, it is. But sometimes you have to go after the unexpected. Sometimes things happen that you don't, like my eureka moment, you don't expect, and you have to grasp that opportunity to have your own eureka moment. And the last thing I'll say is, I like to give a quote sometimes from learned literature a lot of the time, but not today. Today from popular culture. I want to give a quote, from Pirates of the Caribbean from 2007. In our house at home, when my children were young and in early teens, etc., Pirates of the Caribbean became a thing in our house. And I never forget this particular quote. I think it's very apt. When the pirate, Jack Sparrow, the pirate, has made an audacious escape from certain death and certain imprisonment, and he's managed to commandeer a ship and get away. The captain of the Dutch or the East India Company ship is looking very cheesed, and his first officer goes and says, "I think he plans it all out. Makes it up as he goes along." I don't know if you heard that. You might listen again. Makes it up as he goes along. This is what he says. Do you think he plans it all out, or just makes it up as he goes along? That is something that I think is very important. We can have all the strategy and plans we want, but we have to be able to grasp opportunities. And that's one of the key ingredients that has made biomedical engineering in Ireland so great. So I'll say thank you very much, to acknowledge all graduate students and collaborators and my funders, and I'll hand over to Suzanne.
Peter, thank you so much for a fabulous trip down memory lane in a lot of ways, just to track the history and the development and growth of bioengineering over the years, and also in the context of your own pioneering research and how Galway really has grown our graduate base to be able to support the growth in industry as well. Peter has agreed to stay on and take a few questions, so I think we've time for a few. If you do have a question that you'd like to put to Peter, you'll see a little Q&A box at the bottom of your screen, so you can submit your question through that to us. Please don't put it in the chat box because we won't actually see it there. So Peter, just while we're waiting for a few questions to come in, I might take advantage of the opportunity I have being online with you, just to ask, I mean, the growth has been explosive really in this sector, from an industry perspective, but also from an educational and internationally renowned research. Medical devices, I think, it's going through a real challenge time at the moment. The regulatory landscape has changed, but also technology has come on apace as well. So things that you've mentioned, AI and the influence that all of that has on medical device technology, and a lot of the time the regulators are running as fast as they can to keep up with how fast technology is moving. And I think also one of the other big areas that we face is just a massive shortage of engineers generally.
Yes, that is the thing. I mean, even at our 20th anniversary celebration last year, a lot of our industry guests saying, look, we're here because we might pick up some graduates, where are we going to get people? Everybody recognizes this. I think it's important that this message gets all the way down to the homes of Ireland, into the schools, through all the great things that are happening, even down to primary school. It's important that that message gets down there, that careers in engineering generally, in particular in this area, are so plentiful, and the potential is so strong, that there's so many opportunities for people, and not just humdrum opportunities. These are real opportunities for research and development, not just manufacturing quality control, but research and development as well, and new technology creation. So the more opportunities we have to get the message out there, the better. And look, if it takes the government to give more funding to the universities to increase numbers of places on engineering programs and give us more staff, we certainly need these things. We cannot, like, you know, I'm showing you all these 799 graduates, etc., the growth in staff members, but that's really, as any academic on the call will tell you, that's really just treading water. That's really just keeping up with things. We have to grow more in terms of facilities and staff available to teach the students. If that kind of funding can become available, then yes, we should take more people because the opportunities are there for them in employment.
And do you think that there are enough, I suppose, is there enough intake or enough available students, you know, even within our secondary system, you know, just, you know, to give them the visibility to the opportunities that are out there?
I think there is, because I think there is. I mean, I think obviously other, you know, there are other professional jobs and other things that people want to do. Of course there are. And these might lose out. But I mean, you know, when you're looking at 70,000 leaving cert students a year, I think there is the capacity to make a greater impact into that number as to who would come into engineering and into courses like biomedical engineering.
Yeah, I mean, I think for certain, you know, there's almost a guarantee of a very, very rewarding career. Technically,
yes,
opportunities to learn and diversify, but also there is that direct linkage to how you influence people's lives with devices, improving,
yes, it's
saving
engineering,
lives, etc.
It's engineering directly for life. It's not indirect, it's direct. You're improving the life of the human being directly. And that's whatever about anything else, you know, that's what keeps us going, that's what keeps us interested. You know, so I think that's very important.
John, anything, any questions or topics you'd like to bring in there?
I suppose the bioelectronics, and you mentioned at the end of your talk there about you know, ideas for the future, where that's going, and I suppose the healthcare.
Oh yeah.
Side,
oh well, you know, the smart device. I mean, you know, implants with sensors on them. You know, I mean, is a key thing that you implant a stent, you implant a hip implant, you implant a knee implant, you implant. And you know, pacemakers, all kinds of things. The greater extent that those devices can give you live feed information coming out as to how they're doing, how they're you know, what developments are going on, is the disease reoccurring, etc. Lots of technical challenges to do that, but you know, in terms of stent design. In terms of some of these biodegradable stents, wouldn't it be wonderful to have a sensor in there that would be telling you about how fast the degradation rate was going on, or if you have a biodegradable orthopedic implant, for example, a plate or a nail or a screw, you know, rather than having to do an X-ray all the time, you know, how is that degrading? When is the degradation finished? So I mean, you know, I think that is one particular area. You know, that sensing, telemetry, giving back information, real-time information that designers can see it, and in particular clinicians can see it. That's so important, and that's where the link with bioelectronics and medical electronics could be greater forged, I think.
So there's just a question here, Peter. So you spoke about academia, clinicians, and industry. Do you think there is a gap in reaching the healthcare system on the ground, or do you think clinicians meet that need?
I mean, I think well, I think that clinicians are operating, you know, the HSE. I think our clinicians are operating in a very challenging environment. We all know that. I think clinicians are operating to the best extent that they can. Okay, in terms of what they're able to do. I think, but my experience with clinicians, certainly the ones I've worked with, is they're always interested in new things, learning new things, seeing new things and bringing them in. And I think that, be it academic clinical link or industry clinical link, doesn't really matter. You know, particular things like the BioInnovate program, if I go back to that, you know, where you're linking with the clinicians and giving them more information and involving them more in what's going on and what new developments are. Yes, I think they would have an absolute appetite to further develop what they do within the challenging environment that they operate. I should also mention our the physician engineer program that I talked about, physicianeer program I talked about as well, where here in Galway now we're doing the MBBC HBAO, the medical degrees, and the biomedical engineering degree as well. So I think the graduates who are going to come out of that program will be much more in tune with the technologies that are there and what they want to implement in their clinical practice going forward. I've never found or worked with clinicians that weren't interested in talking to me. It's just we're all working in this country in a challenging environment. And I mean, I think that they're always open to opportunities if it's presented and supported in the right way.
And certainly, you know, one thing that I often think about is the general public will think about and will see medical devices and medical technology, and absolutely rightly, they see the clinician who's standing behind it, who's performing the surgery, who's advising them on what they need to do for their health. Is there anything better, do you think, that we can do to make sure and help the general public also see, when they look at a medical device, the engineer, the design engineer behind it, the manufacturing engineer who has produced it? Because I think a lot of the time, you know, we have this fantastic industry. It's imbalanced possibly in the way that it's associated with our fantastic clinicians, and we don't necessarily promote our fantastic engineers.
Yeah, I mean, I think well, I mean, I think in fairness, in terms of, you know, things that are in the media, shall we say, it's difficult to compete with, you know, ER, right? George Clooney and the gang, right?
Yeah.
We're never going to be able to do that, okay? But I mean, I think, you know, and it's more than just the TV arena, into the social media arena, podcasts, short videos, things like this that would demonstrate the interesting activities and the interesting career, and crucially important for society, kind of work that engineers do. To get that out there through the social media channels, through popular media like that, that has to be the way to do it. We're never going to compete with George Clooney, right? But I think that I've always thought that, you know, back in the day when TV was the only way that anybody looked at things, why don't we have a soap opera about engineers or something or other, you know, critically saving lives, you know, building massive windmills somewhere out in Connemara or whatever it is, that would be dramatic. I've always thought there would be a market for that, or at least we could try to get across the interesting things that we do. But of course, we've moved away from TV now. We're into social media, Instagram, Facebook, everything. So those platforms have to be looked at. And then you're looking at short bursts, short snippets. That's key. And then you got to talk to the younger generation about how to do that most effectively. But yes, there's a lot more that could be done.
Brilliant. I think people are starting to probably rush off to their meetings now after lunch. So I'm going to hand over to John McGivney, who is the chair of the Biomedical Engineering Division, to say a few closing words to bring our event to an end.
Thanks, Suzanne. And I suppose it's great to get the honour to propose a vote of thanks to Peter McHugh today for giving us a very interesting sort of whistle-stop tour through his career and the highlights of biomedical engineering over the last 30 years or so in Ireland. And I suppose a couple of things that would strike me. One is the enthusiasm with which he speaks and which he continues to have for biomedical engineering, and how he's trying to continue to drive it forward and looking at, you know, improving, I suppose, people's lives with the developments that are happening in stenting in the areas that he's interested in, but also talked about, you know, medical electronics as well, being involved there. So I think that's hugely interesting. And I suppose we were very lucky in a way that, you know, from his early days doing his PhD in Brown University, you know, that he, you know, he mentioned medical ceramic composites in the auto and aerospace industry, but he ended up coming back to Ireland and, you know, in getting involved with angioplasty catheters and being involved in the biomedical engineering sector. And I think that has been of huge benefit to Ireland and the biomedical engineering industry that he made that choice, and that those few eureka moments happened. I think the mentioning of the funding that started to happen in 1998 probably brought around a huge change to, I suppose, biomedical engineering, and it gave the opportunities to generate the research and set up some of those degrees in the National Centre for Biomedical Engineering Science in Galway. And that was huge, I suppose, impetus given to biomedical engineering. But it still took somebody to lead that and drive that on. And you can see from Peter's own highlights of his own career that he was always the man out front leading that charge, certainly in University of Galway, among others. And I suppose just a huge vote of thanks for Peter today for giving us an insight into that, an insight into how things, get achieved, to watch out for that eureka moment. And as he said at the end, grasp that opportunity if it arises, but you have to grasp it. You can have a plan, but you need to grasp the opportunities when it arises. I suppose if you want to take one message from that today, that is one of the messages I would take myself personally. And I suppose the other thing is, engineers also save lives, and we really need to just promote that out there and get more people involved. So thank you very much, Peter, today. Really enjoyed the talk and wish you well in your continued career.
Thank you very much. Thank you very much. It was an honor. Thank you.
Thanks, Peter.